In working with the trig functions, we come across a lot of times the trig functions are interrelated. There's a lot of times that it's beneficial to change from one trig function to a different trig function. It simplifies an expression or makes it easier to do some subsequent math with. And so we want to talk a lot about trig identities. We're going to start building a library here that will grow throughout the quarter. These are a lot of the basic ones that we're going to see often. Let's start off with our reciprocal identities here. The sine, cosine, and tangent. And this is basically based on their definitions themselves. The secant is defined as the radius of the circle divided by the x-coordinate. If you go to any particular point on a circle, that ratio of the radius divided by the x-coordinate gives you the secant, and that's the reciprocal of the cosine function, which is x divided by r. Secant is r divided by x, reciprocal of it. And so we know that the secant of theta is 1 divided by the cosine of theta. Similarly, the cosecant is 1 over the sine of theta. If you take the sine ratio and you flip it over, you'll get the cosecant ratio. And if you take the cotangent ratio and flip it over, you get the tangent ratio. Or if you take the tangent ratio and flip it over, it's the same as the cotangent ratio. A couple others that come up is that tangent is the sine divided by cosine. That's a very useful one to know, that we frequently replace tangent with the sine divided by cosine. Just to kind of verify that, we know that the sine in that circle is the ratio of the y-coordinate to the radius, and the cosine is the x-coordinate to the radius. So I've got y over r all divided by x over r. So y over r divided by x over r. And when you divide fractions, you flip over that fraction and multiply. And so I get, flip over the second one in particular, y over r times r over x. And when we do that, the r's will cancel off, and we'll get y over x, which is the tangent ratio. We know that if you go to any point on a circle and you take the y-coordinate divided by the x-coordinate, you will get the tangent value, the ratio in there for the tangent. So tangent theta is the y-coordinate divided by the x-coordinate. It's also sine over cosine. And then we can combine that with the cotangent. We can do it with the y over r, x over r thing, or we can work off this. The cotangent is 1 over the tangent. It's the reciprocal of the tangent. So it's cosine over sine. So we have the tangent is sine over cosine ratio, and cotangent squared is equal to, or cotangent is cosine over sine. We'll tend to use that tangent one more frequently than we use the cotangent, just because we see tangent more frequently than we see cotangent. Another type of identities that are out there are the Pythagorean identities, that if you look at sine squared of theta plus cosine squared theta, it's equal to 1. And maybe a little bit on that notation there. Let me clear this up here. When we write the sine with the little squared in that location, when I write out sine squared theta, what I really mean is the sine of theta, that whole quantity raised to the second power. It's just a convenient way to write that down. It kind of helps a little bit with some confusion that if you write sine theta squared, there's some confusion of what that is. Do we mean that that's the sine of theta all squared? Is that what we mean? Well, or do we mean that that's the sine of the angle squared? Are you squaring the angle? So if you're looking at, are you looking at the sine of 3 squared? Is that going to be the sine of 9? Or do we mean sine 3 times the sine of 3 in there? And there's some confusion over that. And so we've gone to putting the little 2 on the inside here between the sine word and the theta. We do it with the cosine as well in there. But sine of theta squared is kind of confusing. What exactly is being squared there when you write sine of theta squared? And the general interpretation, I think, is that we're more likely to think of it. You're meaning that you're talking about the sine, that you're squaring the angle, that you're doing 3 times 3 and then evaluating it as the sine, as opposed to taking sine 3 times sine 3. Okay, but we got the sine squared, which means sine of theta times the sine of theta, plus the cosine squared, cosine theta times cosine theta equals 1. And we can verify that if you want to. We call it the uh, Pythagorean identity, because if we look in we've got our circle that we're dealing with, and you're looking at some sort of angle there, theta, whatever angle you're looking at, theta. I know that the radius of the circle, the x coordinate, and the y coordinate are related by the Pythagorean theorem, that x squared plus y squared equals r squared by the Pythagorean theorem. So wherever you look at in that circle, whatever angle you look at, that the x coordinate squared plus the y coordinate squared is equal to the square of the radius in there. But if you look at the relationship of sine squared x plus cosine squared theta, I know that sine is y over r, so I'm looking at y over r squared plus x over r quantity squared. And so I have y squared over r squared plus x squared over r squared, or I can write that the denominators are the same, so I can write that as x squared plus y squared, all divided by r squared. But by the Pythagorean theorem, I know that x squared plus y squared equals r squared. So this is just r squared over r squared. And a number divided by the exact same number always works out to be 1. So we know that sine squared theta, the sine of theta, the whole quantity squared, plus the cosine of theta. If you square the cosine of an angle, same angle in both of those, and add them together, you get 1. And then there's a couple of variations of that. You can move the sine to the other side of the equation, and you get the cosine squared is equal to 1 minus the square of the sine of theta. And sine squared theta is equal to 1 minus cosine squared theta. So those are our Pythagorean identities. That's the big one. We tend to use those Pythagorean identities a lot. When you see a sine squared or a cosine squared, oftentimes we want to change it out. There are a couple of other identities that are also associated with the Pythagorean theorem. There's 1 plus tangent squared theta equals secant squared theta. 1 plus cotangent squared theta is equal to cosecant squared theta. And there's variations on these as well. You can move the tangent to the other side, so you get 1 is equal to secant squared theta minus tangent squared theta, the tangent of theta quantity squared. Square the tangent of theta. You get that. Or we could do, let's see, we could do tangent squared theta is equal to secant squared theta minus 1. Those are other sorts of identities out there that are useful to use as well, some other Pythagorean theorem identities. And then finally, I've got 3 more identities for us to start with. They are the co-function identities, where the sine of pi over 2 minus theta is equal to cosine of theta. The tangent of pi over 2 minus theta is equal to cotangent of theta, and secant of pi over 2 minus theta is equal to the cosecant theta. So it's the relationship between sine and cosine, tangent and cotangent, secant and cosecant in there. Sometimes useful. Those aren't nearly as useful as the previous ones, the trig identities, the Pythagorean identities, the reciprocal identities that are out there. So let's take a look at using an example, using these identities to simplify an expression. Suppose I have the expression, a complex, well, kind of a long fraction, that 2 plus the tangent of theta, the tangent squared theta, all over secant squared theta, and I want to simplify that. So I want to see if I can get that into something that's a little bit nicer. One of the common things to do if you've got tangent and secant is to replace those with sines and cosines. So let's do that to start with. So I'll have 2 here, and tangent is sine of theta divided by the cosine of theta. So I'll have tangent squared, I'll have 2 sine of theta all over cosine theta all squared. And then secant is 1 over cosine theta, but it's secant squared, so it's going to be 1 over cosine theta, the whole quantity squared in there. So I have 2 plus sine squared theta over cosine squared theta, all over 1 over cosine squared theta. We can bring that square inside the parentheses there. If you square a fraction, you end up squaring the top and squaring the bottom. Okay, we want to clean up this fraction a little bit. We've got some things that are pretty messy, and what I'm going to do is I'm going to multiply. A nice way to, well, we can do. Well, let's do it as a division. Let's do it that way. Let's say that that's 2 plus sine squared theta over cosine squared theta. I've got a complex fraction in there. What I'm doing is I'm dividing that piece by 1 over cosine squared theta. I've got the top is the 2 plus sine squared theta over cosine squared theta, and I'm dividing it by 1 over cosine squared theta. And so to divide fractions, you flip it over and multiply. So that's 2 plus sine squared theta over cosine squared theta multiplied by cosine squared theta all over 1. All right, so I can flip over that second fraction, the one you're dividing by, and then what I want to do is I want to multiply. Let's simplify. Let's go ahead and distribute that through the parentheses there. And that will give me 2 times cosine squared theta plus, then I have to multiply it by the sine squared. And the next one, and the nice thing is that the cosines will cancel. So I'll just have sine squared theta in there as a value. And I might want to see if I can simplify that a little bit better. I've got a sine squared and a cosine squared. Actually, I could do it that way. I could say that that's, well, 2 cosine squared is a cosine squared theta plus a cosine squared theta. That's 2 cosine squared theta plus a sine squared theta. And then that is, I can take 2 of these and say that's the trigonometry identity, and that's 1. And so I'm going to get cosine squared theta plus 1 would be the simplified version of that expression. I'm not sure we can get any closer. We might be able to, but I think that's pretty good there. That's pretty simple sort of thing. Looking up at our trig identities, it's not quite. If I had cosine squared, 1 minus cosine squared is equal to sine squared. So I can't quite replace that one in there. And I think that's about as simple as we can get it in there. Although the 2 cosine squared theta plus sine squared theta is pretty simple, we can get it down to just cosine there if we want to. Cosine squared theta in there plus 1. So that's pretty nice. I think that's about all we can do with that. So there we go. But 1 plus cosine squared, or 1 plus cosine squared theta, is a lot simpler than the fraction that I had up here that I started with, the 2 plus tangent squared theta all over secant squared theta. We get another relationship that's pretty common. Pretty simple. And that's sort of one of the standard practices that we have is one of the standard ways to do a simplification is convert everything from sine and cosine, or from tangent to sine and cosine secant, convert everything to sine and cosine, and then keep looking for opportunities on where you can use the Pythagorean identity. You just follow through with what you need to do to find those Pythagorean identities. Convert to sine and cosine. All right.